Hello, children. In this video, we're going to take a look at what happens if we have a circuit that is a little bit more complex than a circuit with just resistors in parallel or just resistors in series, and that is known as a complex circuit. First part here, I didn't realize I wasn't recording before, so I already drew all this out. But I'm going to go through what we know so far about series and parallel circuits. I'm going to go over this information you see here that we've done in class. Feel free to watch this again, or if you feel good, you can skip ahead to where I tackle a complex circuit. Okay, so things we know. We know Ohm's law. So this is Ohm's law. I guess we could label that because I'm going to refer to it as such. Ohm's law tells us about the relationship between potential difference, the change in voltage, the current, and the resistance in a resistor. And this is for an individual resistor. And we have the power relationship, which tells us the power from a battery, it could be I delta V, or the power from dissipated or lost by a resistor, I squared R. Both of these will work for a resistor, because this is just taking Ohm's law and putting it in here for this delta V. Okay. Then we have series versus parallel resistors. Resistors are in series if they all share the same current. So if they're all part of the same loop, they will have the same current. So these three resistors here are in series because the current is unbroken. There are no junctions or breaks or splits. So they share a current. Notice that they don't all share the same change in potential. They're delta V, unless they're all the same resistor. They'll all have different delta V's, such that energy is conserved. When I go over the battery, I gain a certain amount, and I lose that after going over all three resistors. So mathematically, the battery voltage here, how much I gain has to be equal to how much I lose as an electron would go around, electron would go this way, but as a charge would go around this whole path. It crosses all three resistors as it does so. So together, they bring me back to a total change of 0. Now, if I were to say the current I, the current from the battery, is the same as the current through each of these resistors because it does not change as I go around this loop due to conservation of charge. Because of these two rules, and you can do the algebra using Ohm's law to connect these, we can pretend, if I was just say looking for this current, I could pretend that this is a circuit, the most simple circuit, one battery, one resistor, and this super resistor, my equivalent resistor, is taking the place of these guys. And mathematically, algebraically, it turns out that I can pretend that this resistor, its resistance is just the sum of all the resistors I had before. So if I had 3 resistors, it'd be all 3. If I had more than 3, I'd keep adding them. And that's useful because then I could then go and use Ohm's law with this equivalent resistance to find the current going through this circuit. So that's really why we use this equivalent resistance. It allows us to find the total current easily. Parallel, a little bit different. So parallel, in this case, I have junctions. I have places where the current splits up, so they will not share the same current. What they do share is the same change in potential. They all drop the potential by the same amount because an electron or a charge is not going to go down all the paths, it's going to go down one of the paths. And when it does so, energy needs to be conserved. So it gains in the battery, it loses over the one resistor. So in this case, the change in voltage over any of these resistors, 1, 2, or 3, has to be equal to the voltage supplied by the battery. The currents, however, I know this current is my total current. The battery has to provide enough that each of the resistors gets the current required to drop the voltage by that amount. So you can see I have the total current, and then it splits into these 3 paths. Which means if charge is conserved, if a certain amount of electrons are moving out of this battery, and they're going down different paths, overall, I have to have the same amount of electrons moving every second. So these three paths added up have to be equal to my original path. Again, using algebra and Ohm's law, we can find then, if we want to pretend again that this is one circuit where the current is just the current from the battery, so these are still the same, we can pretend we have one equivalent resistor. The formula is a little bit more complicated. 1 over the resistance of the equivalent is equal to the sum of 1 over each of these. What this formula says is that as I add resistors in parallel here, as I add more, the equivalent resistance actually goes down, because this current, as I add more paths, I get more current, which means overall I need less resistance. So that's kind of weird. Adding more resistors decreases the overall resistance in parallel. Okay, so those are the rules as we know it. Now let's look at this circuit, a complex circuit. It's a combination of resistors that some are in parallel, some are in series. It's a little weird. We gotta break it down to really know for sure what's going on. Now I can't just apply my rules that I did before, because these do not all follow the same rules that they did in these cases. So this resistor, let's look at this 16 ohm resistor. It does not share the same current with either of these. As I go through here, they do not share the same current because the current will split at this junction. Likewise, it does not share the same potential voltage, so it's not in series with them. It also does not share the same potential change, the delta V. This will change it by a different amount than these resistors, probably. So the math is very, very specific. So I can't say this resistor is in parallel with these two. Let's actually color code this to make that more obvious. So I gain 10 volts. This first resistor is going to take away some of that energy, some of that potential. And I know at the end I have to be back at a total change all the way around. I have to change it by 0 overall. Looking at this, I can see these are going to drop their potential the same amount. But it's probably different than this. If I draw the currents, I have the full current come from the battery. So it's going all the way around this loop. And the 16 ohm resistor is receiving the full current from the battery. But then it's going to split as it goes here. I may get some I down this way. But we should label, let me call this resistor 1, resistor 2, and resistor 3. Which would make this I2 and I3. I'm not going to label this one as I1 because I know it's the same as the total current, so I don't need to have another name for it. So here its current is splitting. It's splitting into I1, and splitting into I3, and those are going around, and then they meet back up together into I. All right, so I can see none of these resistors share the same current, so they cannot be in series. These two, however, I can notice looking at my diagram here, they do change the voltage by the same amount. So while all three resistors together are not in parallel with one another, these two are within parallel. So our first goal when doing a complex circuit, our steps, let's talk about what we did so far. We identified these areas that have the same voltage. So we color-coded, we labeled our equal potential lines, we would call that. This has the same potential. All these spots here have the same potential, and these all share a potential. Okay, so label or color potentials. All right. We also labeled the currents in each section. So we saw that the current was going to split, and we labeled that as well. Okay, so now what we're going to do, now the first new step, this is stuff we could have done for old circuits, is we're going to look at, okay, are there any resistors here that do share a current or do share a potential difference? If they share a current, they'd be in series. If they share a potential difference, they'd be in parallel. And we can find those and we can start combining them. We can start sticking resistors together as equivalent resistors. All right, so we're going to look for resistors. It could be 2 resistors, it could be more. Look for resistors in series or parallel, using our rule that if they're same current, they're in series, same delta V, they're in parallel. Then we're going to combine them into equivalent resistors. Combine into equivalent resistors. So let's do that. I noticed when I was doing this before that these are in parallel. They are changing the voltage by the same amount. Even if it's not the whole voltage from the battery, they're still going from the same voltage before to the same afterwards, the same drop. So I'm going to combine those using my parallel rule. So my parallel rule for an equivalent resistance. So my goal is now I'm taking this circuit, and this guy is staying the same. I'm not messing with him right now, 16 ohms. I want to combine these into an equivalent resistor, and I could call it R23. It's a combination of resistors 2 and resistor 3 there. And I can use, to do that, I know 1 over R equivalent of 2 and 3 is 1 over R1 plus 1 over R2. And in these examples, I tend to make the math work out easily for you. Be prepared for that not always to be the case. So I'm going to get, that's 1 over 6 plus 1 over 12. This is the same thing as 2/12 by multiplying by, that's a good way to do it, to write it. I'm going to multiply each side by 2. So I'm going to get 2/12 plus 1/12 equals 3/12. So that's 1 over. So here's a big mistake I see students make a lot, is they'll then say, okay, my equivalent resistance is 3/12. That is not the case because this is 1 over. I have to flip this number at the end to figure out what R23 is. So R23, if I invert both sides, is 12/3 or 4 ohms. All right, so I can say this is a 4 ohm resistor. And please notice again in parallel, I had a 6 ohm, 6 ohm here and a 12 ohm here. Together, they act like something that's only 4 ohms. That's less than either one because this is 6, but I added another path. Even if it was a more difficult path, there's still another path. So overall, the resistance drops. All right, now I could go and color code this one. This is still, oops. When I do so, I'm going to match my colors that I did before because that shouldn't change. All right, so now I have a very simplified version of this more complex situation because I look at this and now I say, I'm going to repeat my steps. I'm going to repeat this. So you do this, step 3, and then you go back and you do step 3 again until you find whatever you're looking for. Okay, this is 2 things in series because I look now, I have 1 loop. They just have that total current from the battery. Great. So I can just say this was still R1. is some equivalent, and this is a combination of resistors 1, 2, and 3, so we could label it like that. And we know R1, 2, 3 is going to be R1 plus the equivalent of 2 and 3. So we have 16 and 4. 16 ohms plus 4 ohms equals 20 ohms. All right. Voltage was 10 volts. Might as well throw this on here. You'll notice when I do this, I now lose some information about this circuit. It's wrong color, blue. I lose information about this intermediary bit here, because now when I shove these together, it's now going from blue to red directly. Great, and I still have my current I. And I can solve this. This is a very straightforward Ohm's law sort of dealio. I define, if I call this 0 potential, it makes this, I gain 10 potential. So my resistor, my delta V for R1, 2, 3 is 10. It's taking away 10. It's going from that blue to red, so I can say delta V 1, 2, 3 equals IR1, 2, 3. So 10 volts equals I, 20 ohms. I get a current of 0.5 amps. Excellent. So I've now found the current through this circuit. And because of how I've done this, because I've been looking for this total current I, which is the current from the battery, that hasn't changed. Regardless of what I do to combine these resistors, I'm just looking at them a different way. It's still the same circuit. It's still the same total I from the battery. So knowing this I can now go back if I needed to. Maybe I just wanted to find the current. Maybe I'm done. But I can now find other things. I can now go back and I could find how much the 16 ohm is changing the potential by. I could figure out what I2 is, what I3 is, based on that information. Let's do that. Why not? I'm going to, so that would be step 4. So we did this. We did this until we find I. Let's do that in green so we know what I we're talking about. Step 4, find whatever else you want to know. I'm actually going to move all this over. Getting so good at this drawing on tablets thing. So I have some room to find that other stuff for this resistor I have here. To organize myself, because I have a bunch of different resistors and currents and stuff, I'm going to make myself a table. R, I, delta V, power for each resistors 1, 2, and 3, and then I have the battery. I don't usually include the battery in my table, but I'm trying it out, seeing how it goes if I do. Great. And again, this writing it this way helps me mirror, because I know Ohm's law, delta V equals IR. I can see that here, delta V, IR, so this box times this box gives me this box. And P equals I delta V, P I delta V. So this box times this box gives me power. So this is a nice way of organizing all my information. It makes it clear to me what I know and don't know. So I know all these resistors, so I'm going to fill. The battery doesn't have a resistance because it's a battery. I'm going to fill those in. One is 16 ohms. Just because I drew this too small, I'm not going to write the units. 2 is 6. R is 12. I can't. I got to have units. I can't tell what these numbers are otherwise. Great. Do I know the delta V's? Going back, this is going to be 10 because we say this is 0. Battery gives 10. But I don't know this purple bit. So if I don't know this, I can't find these delta V's or this delta V easily without knowing something else. What else do I know? Well, I just found through this complicated process of simplifying my circuit, I now have this. I had to do this first because now I know what that total current is. So before, this would have been my table. I know one thing. I know the resistances. And I know the voltage from the battery, I guess. So let's add that. 10 volts. I don't know enough to solve any of these rows because I need two things in a row to figure out the rest using my relationships. Now that I did this, and now that I found this I can say, well, this total I found was ½ amp. That's going through resistor 1 in my original circuit. So resistor 1 I can add, not 1 amp, ½ amp. I can add that at 0.5 amps. And this opens up a lot of new possibilities for me. Put in this piece, it's like doing the corner pieces first in a puzzle, you know? Oops. Because I say, oh, now I know it has a resistance of 16 ohms, it has a current going through it of ½ amp. I can find what its change in potential is. 16 ohms times 0.5 amps, its delta V is 8 volts. So start with 10 is taking away 8. It should make sense to us that this is a pretty big proportion of 10. Because when we looked here, we saw this is the bigger resistor in our more simplified circuit. Okay, 8 volts. And whenever I add something to my table, I go back to my diagram. And I say, does that change, give me anything in my diagram? Changing it by 8 volts, that does. 10 volts changed by 8. 2 volts. Excellente. So I've added something to my diagram. I've added that I can call this 2 volts. Having defined this as 0, I gain 10, I lose 8. 2. Now I say, does that help me with my table? We're kind of bouncing back and forth here is the idea. 2 volts to 0 volts is the change for both of these resistors. So I can add that to my table. Notice that the change in voltages are different than the voltages we write here usually, except in this case when we're going from 0 to whatever is right before 0. Okay, added those to my table. And I can now find these currents. I know R, I know delta V. I is going to be delta V divided by R. So 2 volts divided by 6 is a third. 1/3 amps. 2 volts divided by 12 is a 6. 1/6 amps. Okay. I can check my work. I know that I is splitting into these two. So this is 0.5 or 1/2. What's a third plus a sixth? That's 2/3, or 2/6 plus 1/6 is 3/6. 3/6, well that's 1/2. Good, I've conserved current. So always be checking your work, making sure your rules still apply. So total current split into these two. These two do in fact add up to my total current. Great. And we could have added here that this is also 0.5 amps going through the battery, because that was the total current that we found. All right, and then I can now go and find the power. P equals I delta V. Oops. So let's just plug in this times that equals this, that equals, I guess we'll do it. 0.5 times 8 is 4 watts. 2/3 watts. 1/3 watts. 5 watts. And again, this is an opportunity to check my work. Power from the battery, it's adding a certain amount of energy per second to the circuit, has to be equal to the total power taken away. So only in this column can I make sure these add up to this. Notice that's not the case here, so don't try to do that for these. Only in this case, total power from the circuit, power given by the battery, power taken by the resistors. 4 plus 2/3 plus 1/3, 5. So all the math checks out there. We can check this column by saying I have to go around a loop and get 0. So I go around, gain 10, lose 8, lose 2, I'm back to 0, great. Gain 10, lose 8, lose 2, back to 0, checks out. And we already checked before that the currents work out with our main rules there. So this is a complex circuit. We have solved this complex circuit, great. Other situations could involve maybe not being given a resistor, instead given something else, and then our procedure is going to be a little bit different. But this main procedure here, I just realized I stole these ones. This main procedure here is going to let us, this will always work in a situation where we're given the batteries and we're given the resistors. This process will let us always find everything else. If you want, I think we'll stop there. We'll stop there. We'll do examples. You'll work through your own in class on Monday or Tuesday. Peace.